Okay, as you remember on Thursday, I mentioned that the relationship between gases is this is called the ideal gas. It's ideal designed to be a very low pressure. When you high pressure, this medium is quite so that you don't hurt before you start getting away from low pressure. And he said we talk about why. Okay, so these are the variables. There are four of them plus a constant. Now, I'm going to give you that on test 5. You don't have to memorize it. You won't have to memorize it for 1A. It's not too hard. The tricky part is R. That is a constant that works out all the dimensional analysis. And that's going to depend on what units of pressure you use. In my opinion, the easiest unit of pressure is and that's what you're using here. 1 atmosphere is where we are probably a little less than the valley, second round, and 1 atmosphere. And otherwise, there's inches of mercury, millimeters of mercury, Pascal. Those are the 4 main uses. And then the R value that's going to be different for each one. The one we use is atmospheres, and that's the one. All right. So a couple things. Now, in your lab, you're going to be doing this week, you're actually simulating a gas situation where you can add molecules of gas into the thing and watch the parameters change. You change the volume, you change the pressure, you do all this stuff. You see how everything kind of moves around. But there's a couple things you need to get out of this. One, pressure and volume are indirectly related. One goes up, the other goes down. Okay? Indirect variation. Direct variation, indirect variation. Also, it's called a directly related, indirectly related. Okay, so when pressure goes up, volume goes down. When volume goes up, pressure goes opposite. Okay, and then pressure is directly related to temperature. Pressure goes up, temperature goes up. Volume is also directly related. These 3 relationships are going to be honed in quite a bit on your lab. Okay. As I mentioned last week, temperature is Rankine. And that's absolute temperature. Now, to convert centigrade, Celsius Rankine at 270. Yeah. Oh, excuse me, Rankine is Fahrenheit. Thank you for pointing that out. I took thermodynamics in graduate school. I took it in the engineering department. Fahrenheit. Engineers do everything differently. Really differently. Okay, and so Kelvin. And again, temperature is a metric used for the kinetic energy of the molecule. So all molecules except at absolute zero move around. The kinetic energy is the energy of motion. So if you've got a big molecule, it's going to move slower than a small molecule. Get the same amount of energy at the same time. One's bigger, one's slower. One half, then you split. Okay. So you need to know this. And of course, that's also the same relationship. The simple complementary. Okay. I notice all of these elements. Notice one thing. Volume is in liters, not milliliters. Temperature is Kelvin. That's volume. Milliliters. Now, frequently, questions will be given. If you have such and such a pressure, such and such a volume, what's the temperature? The volume is solid T. With the static situation. Two, another question is if one can change the condition, one can do the other. What that means, the pressure or the volume, or one can change it. And those are the two main types of problems that we work with. Okay. For static, you can be just be using PV is equal to R nRT. So that's static. Now, this is derived from okay, so condition 1, PV is equal to nRT. Condition 2 is that. So what's constant here is the nR is constant. So if you change condition, now we can set these two equal to one another. So if we solve for nR, so all we're doing there is just solving for nR, because those are the constants, both of those changing situations. So now we can equate the nR's together. That means and that's how they derive this changing condition. Okay, so PV over T, condition 1 equals PV over T, condition 2. Now, you're not responsible for this derivation, but you do need to be able to work problems using this guy here. But that's how they got it. Okay, so let's look at problem. This is a typical problem. Okay. Now there are 4 variables. If you have 4 variables, how much information do I need to give you before you can find missing? Great. 8 minus 1. 4 variable, I have to give you 3 bits of information to find that 4. If you have 29 variable, that gives you 28 bits of information to find. So, with the ideal gas law in static conditions, there are 4 variables: moles, pressure, temperature, and volume. In this problem here, they're asking you to find the volume. All you're going to be doing now is solving for V. And you just plug it in. Okay? So the number of moles is and then R is going to be 0.85. Which kind of means R is 0.821. It is. Now, R is a constant. Depends on the value of it, though, depends on what units you're using. There's one for milliliters, one for liter, there's one for millimeters of mercury, there's one for inches of mercury, a whole bunch of them. The one we're going to be using in here is this one here, 0.821. Yeah.
Good, 0.21.
Okay, what's missing now? We need temperature. Now, this is nice because they gave you Kelvin temperature, 315. Had they given it to you in centigrade, then you need that 273. And the pressure was 137 atmosphere. So the volume, the volume is going to be in liters. Oh, turned it down. Or 3-6. Okay, so it's just a matter of plugging into that PV. So this is an example of static situation. Give you some other, now what is it? One atmosphere. I've got interesting stuff going on in my life. What's that worse? Okay. That My son-in-law. Okay, so in the future, you'll probably be hearing more and more about MRSA. To treat it, they have to give you extremely strong antibiotics. There's also a tuberculosis that started in after World War II in Russia. And there's one variant, non-curable. You get it, have a nice day. And it's because it was treated with insufficient antibiotics. What happens is it kills 99% of the bacteria except for 1%, and 1% then grows. Those are 1% was when they survived the antibiotics. So now we have a whole bunch of ones that can survive the antibiotic. You use another antibiotic. And half or 1% survive. They keep growing these superbugs. Now we're at the point where there's certain types of tuberculosis that improve. Because we use antibiotics to prevent. So but the CA technical required, you get the hospital, then community that's CA. You got to start. Okay, so anyway, so sometimes I'm a little spacey. That's not an excuse, I'm just saying that's reality. Okay, so are there questions about this problem? You guys have any problems for whole semester? This should be very strict. You just have to recognize when to use it. So when conditions are not changing, that's when you use the PDs that run out. When conditions are changing, going from one to another, then you use this guy here. So let's do an example problem with one of those. Let's see here. Okay, so I'm going to change the pressure now. I'm going to increase the pressure. I'm going to keep the volume, though, the same. And I'm going to jack up the temperature because when you increase the pressure, temperature goes up because they're directly related. So the temperature, let's say, is 46 degrees. And N is equal to. In fact, let's, calculate what the new temperature is going to be. Okay, so the pressure goes up. The pressure goes up, and we're directly related to temperature. And the temperature is going to go up. We don't know how much yet for that point. Volume stays the same. The number of moles, we haven't added or deleted any mass in there, so the number of moles. So basically, we've got. Okay, the pressure is going to be 1.1. The volume is 3. Temperature is 23 plus 273 is going to be what, 296. Okay, so that's condition number 1. Number 2 is pressure went up to 2.1. Volume stayed the same. And we don't know what the new temperature is. Okay, so all we're doing is we're doing plug it into that formula there. Can everyone see where I found everything? Okay, so what we're going to do now is we're going to solve for T2. This is going to be T2 down here on the bottom right. Okay. So we can do some magic in algebra. Cross multiply. So we end up with so we cross multiply here. Right. And this is still over 296, so we need to now then we need to multiply both sides by 296. We're looking at where did the 3 liters go? Yeah. We won't get any different results. Okay. So hopefully I simplified this for it. Here, let me see. Um, yeah. Okay. So we predicted temperature was going to go up. It's a matter of practicing. Remember. And then for gas, one end is really complicated to learn. Basis is yeah, distribution of velocity of gas. Mixture, mod pressure. A lot of nuance in gas. But the best molecular gas started doing problems to this. And that's why I want to give our background. Right. All right, that's what I want to do. I also posted in modules for unifies in the chapter comments. Look those over. Do the one I don't know in the way you want to do. Basically, from my daughter, and then one of my friends. This one going five thoughts. Um, yeah, there was. I didn't see any before. Yeah, I told everyone to send it to five. I did actually, but I did it, I saw the early on, and I just did it, I just didn't know. I threw it in, and then I just did the other, I wrote it down, I don't know if it's with this one. Yeah. Okay, perfect, thank you. No. It's a simulation on your home computer.
Okay. That's fine. So see you on Tuesday then. See you on Tuesday, next Tuesday.
Yeah. Have a happy Thanksgiving and a happy puppy.
Happy Thanksgiving. It's gonna be fine.
Yeah.
Simulation. Where is it?
No, no,
Oh.
go on your laptop. It'll give you a link. It's a- believe that, it's a PHET.com.
Okay, I might have to get that from someone else because I'm working off the PDF. I never was able to get my. own suite. So, once we complete the simulation, how do you set this up?
Just do the library.
Okay.
And I'm not, I don't remember, I'm not gonna look at it. You gotta give me the link, otherwise.
Yeah, I hope, I mean, I'm just gonna ask Jack or someone that has the book for the link.
Yeah.
Yeah.
Okay.
Did you actually have my